So we're going to be looking at classifying triangles. First, we will look at classifying the triangles by their angles. Angles. This may not make a lot of sense right now, but hopefully by the end we will. Okay. Actually, before we... Well, no. Yeah, let's look at the angles first, and then we'll talk a little bit more about triangles as well. So these are not going to be triangles. They're just going to give you angles. Angles, as it turns out, is a way that we kind of measure the space between two lines. For example, yeah, that's good. If this is my line right here, then I would need another line with this one right here, and we should touch like this. Okay. The angle is kind of like if I were to take this line right here and rotate it into this one. So we kind of show this with a little arc right here. And this would be the angle. Specifically, it is measured in degrees. This one we don't know. I mean, to me, if I were to gauge this one, I would say it looks a little bit less than 90 degrees. But we'll talk about those specifically as well, because there's a few specific types of angles that we need to consider on these. Degrees, by the way, are shown as a label with kind of like a little circle. So for example, if this one was 85 degrees, we'd put 85 degrees. That symbol is the degree symbol. Bam. Well, then we've got these different types. An acute angle. By the way, instead of writing the word angle, we're going to show this symbol instead, because if we wrote the word angle all the time, well, we'd probably go nuts. So we're not going to. We're just going to write the symbol instead. That would be read as acute angle. That's a good question. If you wanted to write angle in this whole unit, then that's fine as well. But I am going to be using the symbol. So an acute angle is an angle that specifically is less than 90 degrees. All right, so the question then becomes, what is a 90-degree angle? Let's look at that. So a 90-degree angle is extremely special, but we could also call it a right angle, like these right here. All right. So a 90-degree angle is one that connects to another line. Now, we use the word perpendicular on this. It kind of creates a T on this stuff right here. So if this is my line, let's draw a line up in here. This one. Then a 90-degree angle would be created by this line right here. And we show 90-degree angles, instead of using the arc like we did up there in the degrees, we use a box. Oh, that's not. There we go. A box like this one. This indicates that that angle right here is 90 degrees. Bam. This one is a right angle. So that is where the angle is exactly 90 degrees. This is also known as a perpendicular relationship between the two lines. That's kind of a big word. I may use that often sometimes in this unit. Perpendicular just means that we have a 90-degree angle between two lines. All right, so let's look at what an acute angle is then. So an acute angle, let's look at a 90-degree angle first. That's what the heck. Look at these. So this is my line right here. Then my 90-degree angle would be something like these. Now let's just keep this line, but we're going to compare it to the line that we'll draw. So I'm just going to make that a dashed line. And we need to make another line at this connection, or this point where the two lines intersect. That would give us some degrees less than 90. So I may draw a line like these. Well, that's straight enough. And this would be the acute angle. Alright, so that angle is acute. We have a 90-degree angle. As it turns out, we have another type of angle. And this one is called obtuse. An obtuse angle is where the angle is more than 90 degrees. Bam. So to make an obtuse angle, let's go ahead and do the same thing we did with the acute angle. Alright, so here's a 90-degree angle. But if I wanted an acute angle, I'm sorry, this is obtuse, then I would maybe draw from the point of intersection right here, this line right here. See, once again, we can see this angle. It includes the 90-degree angle, but it goes a little bit further than that. And this one is considered obtuse. Now notice if we combine these, we may look at this a little bit differently. And if we look at this angle right here, what type of angle is this one in red? Yeah, that one is acute. Same if we go up there to the top part. This angle with the acute angle, this one would be considered obtuse. I apologize. There was one more angle relationship we should be aware of. A straight angle is exactly what it sounds like. Let's find a straight angle. Bam, I found it. There it is. This is a straight angle. Now this can be a line, and then there will be points on this line, maybe, to show that this angle right here is a straight angle, which also has a value of 180 degrees. So some of you guys notice if I combined two 90-degree angles, or two right angles, I would get a straight angle up in here. Now notice we haven't even looked at the triangles yet. But this is important as well. For a straight angle, if that angle is 180 degrees, then this one also must be 180 degrees. Bam. And this is, we'll label that 180 degrees. So now if I looked at this whole thing right here, that shape right there that we created is a circle. So how many degrees are in a circle? Well, we had 180 on the top and then 180 on the bottom. 360 degrees. Bam. That's why they have that phrase. Well, I guess I don't know if that's a phrase, but 360 degree turn, then you're just facing in the same direction. Yeah, only one of these triangles can ever have the straight angle, but triangles can have obtuse angles, or right angles, or acute angles. And of course, we would measure these in degrees up and here. Alright, so we will be classifying the triangles by the angles. Alright. So let's consider a triangle up in here. What exactly is a triangle? Bam, that sounds great. Bam, there we go. So the shape must close, and then we would have three sides and three angles. So let's look at something like these. Is this a triangle?
No.
No. Why? Yeah, it's not closed. We do have three sides though, but we may also see that there's not three angles. I got this angle, I got this angle right here, and maybe this one's 90 degrees, who knows. But I don't even have a third angle on this thing, okay? Alright, so let's look at an actual example of a triangle. Like these. Bam. See, now I've got this angle. Now when angles are different, and we should consider this right now. So this is an angle mark that I put in this triangle. If I wanted to show that a different angle was different than that one, then I would show two marks, like this. Alright? Now if I wanted to show that that third angle, maybe it was equal to that first one, then I would give it the same mark, like this. Alright, now I've got these two red angles which are equal, and then this other angle which is different which is why it has a different number of marks. Now, if that third angle is different, I can color it, which is great, but I would give it, instead of 2 marks, because then it's equal to that other one. If it was different, then I would give it 3 marks, like this. That's the notation for this stuff, okay? So you guys have to get used to seeing these marks, because we'll have to denote the triangles this way when we have abstract situations where we don't know the exact values. Alright, so this one has 3 sides and 3 angles. Don't be picky on me on that corner stuff, right? Like I missed that part. And say, oh, it doesn't close, so it's not a triangle. If I mean for it to close, then I will make it close. If I mean for it not to close, then you'll see one like that last example where it's very obvious. Alright, as it turns out, triangles have these corners, right here, which we can use points to show those. Alright. Now, triangles are named by these points. For example, let's just randomly put some letters on these, I don't know, these 3 letters. Chosen randomly, okay? Well, this would be considered triangle, which we don't write the word triangle, we just draw a triangle, kind of small like this. Triangle, this would be considered triangle U-T-E. Oh, that turned out pretty good. That's a beautiful triangle. All right, so this one would be considered triangle Ute. That's the best. Oh yeah, that's a good question. So as it turns out, and some people would say maybe this is triangle T-U-E. But then it looks like Tuesday, and we're more Friday people, right? So, yeah. But this would be acceptable. If I saw that you named this triangle T-U-E, that's okay. Yeah, any of those work? So there would be 6 different ways we could name this, as it turns out. I think this one at the top here is the best, though. I'm going to go with that one. This is just naming triangles, by the way. Classifications is by the angles, like we talked about, but also... Alright, so the sides is another way that we will be classifying at these. Alright, so the first one that we're going to be looking at. Alright, let's go back to this angle stuff, and we'll look at triangles with these specific angles. Okay? Alright, so let's look at specifically an acute triangle first. An acute triangle, like at these. So an acute triangle will have all acute angles. Bam. So let's draw an example of an acute angle, a triangle rather. So I got this one, maybe a D's and a D's. Now this one may look close to 90 degrees, but it is not. This one, maybe it looks different, and then this one is different as well. So all 3 of these angles appear to be less than 90 degrees. So we would consider this one to be an acute triangle. Alright, the next type of triangle for the angles would be, let's say, a right triangle. A different color. So in a right triangle, we will have one 90-degree angle on a D's. So it should look something like a D's. Now, to specify that this angle is 90 degrees, we should use that box to show it. Alright? And then we got those other 2 angles. Maybe they're equal, sometimes they're not. So then we got this one with 2 marks. So this one has one right angle. What type of angles are these other 2? They're acute, right? So the question is it possible to draw a triangle with 2 90-degree angles? Oh, see, watch this. 2 90-degree angles, that's all I need, right? Bam, there's 1. Bam, there's 2.
No, that's not. Oh, wow. It's not.
Why can't we get 2 90-degree angles in at these? Yeah? We can't get this thing to close, which as it turns out is the definition of a triangle and has to be closed. And we can't add more sides to it, like if we added another side like this. Now it is a quadrilateral, not a triangle. All right, an obtuse triangle has one obtuse angle. Well, so here's another challenge, which you guys should enjoy and do, is draw a triangle with two obtuse angles.
Okay.
That's very good. So, as it turns out, let's say that we're going to start with this line. Then, if we had this obtuse angle, right here, and then we said starting from this point, we'll make another obtuse angle. Bam, there's another one. See it? Well, once again, we'd need another side to close this thing, which again is not a triangle. All right, so then let us draw one that is an obtuse triangle. All right, so I'll start with this line right here, this one right here, and all I must do is connect these two endpoints, right, because we got this one and this one. And there is an obtuse triangle because we have this obtuse angle right here. Nailed it. Obtuse. Now again, if I label this maybe what would be the name of this triangle?
Jam.
Triangle jam. Bam. That's a good point. So we saw that we can't have two right angles and we can't have two obtuse angles. What this means is that all triangles have to have at least one, let me rephrase that, at least two acute angles. All right, we're almost there. That classified the triangles by the angles. Let's now classify it by the sides. Bam. So yeah, let's start with the equilateral, which is a big word. An equilateral triangle right here. Well, an equilateral triangle has all sides equal. Now, I'm using the word equal. Eventually this will change into what we call congruent, which we use this symbol. But for now, for our purposes, we'll just say they're equal so that maybe they're a little bit easier to understand for us. But just know in the future that congruent stuff is coming. All right, so let's make an attempt to draw an equilateral triangle. Bam, bam, bam. I nailed it. I got it. Now, this may not be exact as it turns out, which is why we can mark the sides the same way that we did the angles. Now what I need is to show that all the side lengths have the same length. So I would use markings like this one. But if this one is marked with one mark, then this one would be marked with one mark. And same with this one. See, it looks like a Samurai Jack thing right there. But with a triangle instead of a square. So this one we would know is equilateral because all three sides have one mark. Bam. Next one is the isosceles. There's a slight possibility I spelt that wrong. It's missing an E?
Yeah.
But then I got two E's.
No, and then there's an L. Okay, it's I-S.
Isosceles. I nailed it. Isosceles. All right. An isosceles triangle has two sides that are equal. So when we draw these, maybe we got something that is obtuse now. And we could show that these two side lengths are equal. But then we got the third side, which must be different. Like these. Now again, we should mark it to show that it is different. 1, 2, bam. Now we can see that it is different from the other two sides. So if we were to classify this one that we've drawn, it is clearly isosceles, but it is also obtuse. So this one would be considered an obtuse isosceles triangle. Is it possible to draw an acute isosceles triangle? Sure is. Let's look. So let's say then that we have these two side lengths that are equal. Then we would have this other side length, which is not equal. But this one would give us certainly an acute isosceles triangle. So what do you guys think? Is it possible to get an isosceles, a right isosceles triangle? Well, let's draw her one then. So I got my right angle. Are these two sides equal? We'll say that they are. And then we just got to connect those last two parts, right? So then we got something like these. Bam. And we see that we can create an obtuse, an acute, or a right isosceles triangle. All right, and that brings us to the last classification based on the sides. That is called a Scalene triangle. Triangle. Again, the spelling may be a little off. I'll take it, whatever. All right, a scalene triangle has no equal sides, which really is just a short way to write that all the sides are not the same or congruent. So, or we could say that all sides are different on this one. So let's go ahead and draw us a nice scalene triangle, something like these. I got a really short side right here. Bam, got it. This one is different from this one. How do I know? Because I showed with the markings.
Okay.
Bam. Yeah, so even though these two sides may look the same, having marked them differently shows that they are indeed different.
Okay.
So yeah, we would mark these only when we don't have the measurements. But sometimes we'll be given the measurements, which is great. All right, so let's label these. Yeah, this is a good one. What would we name this triangle? Yeah, maybe we label triangle bat. Yep. And maybe this one up here. Maybe this one would be labeled man. Then we got triangle bat and triangle man. So if we combine them, then maybe we get Batman. I don't know. It would be especially horrible if we combine those two triangles and got Bruce Wayne. That'd be really weird. Here are these. All right, so we went over the classifications already. We don't need to look at this. That's what we just barely done. But let's take a look at these questions. Is there more than one way to put together a triangle with three specific lengths?
Yes.
No. No, that's a good thing as it turns out, because if I gave you three side lengths, you can make one triangle and that is all you could make. You could make two triangles. You could maybe, for example, well, let's look. All right, let's say I had this right triangle. Well, I could duplicate it right here.
And make it different.
I could turn it, but I still have the same triangle right here. Okay? I could flip it, I could rotate it, I could turn it upside down, but I would still have the same triangle no matter what. I've just rotated and transformed it in certain ways, okay? So as it turns out, what pattern do you see involving the sides of a triangle? Bam, there we go. If we're given three specific side lengths, we can only make one specific triangle on that stuff, right? We're going to look at this number 3 here in a later lesson, but not today, okay? Well, but I guess I'll give you the answer anyways. The sum of the three angles is always 90 degrees, which allows us to use an equation for that. So I said 90 degrees, dang it. I meant 180 on that.
What if it's obtuse?
Yes, 180. That'd be better. Not 90 degrees. So, for example, if I told you guys that, this is what this leads to on this, is let's say that angle 1 is 90 degrees, and then angle 2 is, let's say, 80 degrees, then what would the measure of angle 3 be? 10 degrees, right? Because all three of these have to add up to 180 degrees. Now there's something else you guys will see in this unit is an M in front of that angle. And it should be the case for all three of these because we have the measure of these three angles, and that's what the M stands for. The measure of angle 3 is 10 degrees. Right here at the end. For that first one, the measure of angle 1 is 90 degrees. Another notational thing. Alright, for each group of 3 side lengths in inches, determine whether a triangle is possible, right, yes, no, and we'll justify our answer. Let's look at what this is really trying to say. As it turns out, for all triangles, the 2 short sides always have to add up to more than the big side. Okay? This is true always. Here's the problem is if I had the length of a side and the other 2 sides were just as long, see, then as soon as I put some kind of angle on those, then they probably won't connect. Okay, because they're not long enough to connect. Because the shortest length between 2 points is a straight line. So if I lengthen these, then they have to be automatically bigger than that third side right here. That may not make a lot of sense right now, but hopefully these examples will help. If those 2 shorter sides are shorter than the long side, then it can't create. As soon as we put angle on them, then they'll just never close. It will never close the shape. That may sound better. Let's look at these values then. So remember, the 2 short sides have to be more than the big side. So my 2 short sides on this are 14 and 2. So 14, I'm going to have to add them together. This is 16. Is 16 more than 15 and a half?
Yes.
Yes. So could we make a triangle?
Yes.
Yes. Bam. Well, on B, all 3 sides are the longest side, but all 3 are also the shortest. So I'm just going to choose any of the 2 sides, and when I add them, I need it to be more than the other side. So let's choose these 2. That would be 1 plus 1, which is 2. Is 2 more than this last one?
Yes.
It is. So could we make a triangle?
Yes.
Yes. That's a good point. B right here is equilateral because all 3 sides have the same length. Alright, well you guys try C then. Very good. So on this one, the 2 short sides is 7 and 7. So we're going to add those 2 together. We get 14. Is 14 more than 17?
No.
Nope. Therefore, this one is no. You could not make a triangle with these 3 side lengths. Number C, letter C. What type of triangle is it?
It's not a triangle. Yeah.
Oh, yeah, it's not a triangle. I'm sorry. If it worked out to be a triangle, what kind of triangle would it be?
It would be acute.
I got isosceles, right? Because it has 2. It would have 2 equal sides. If it could make a triangle, but it doesn't. Thanks for that. D? Well, we got to look at the 2 short sides, right? 3 and 4. And 3 plus 4 is 7. And 7 is not bigger than 9. Therefore, this one is no. Yeah, if we could make it a triangle, it would be considered a scalene. All right, what about E? Yeah, what are the 2 short sides on this? 5 and 4. 5 plus 4 is 9er, which is bigger than, let's put it on my desk. It is bigger than 6 and a third. Yeah, so yes, you could. This one would definitely make a triangle. Bam. All right, F is very different because the 2 short sides are 2 and 1, so when I add these, I get 3, right? Well, 3 is not bigger than 3. Therefore, this one would be a no. It's got to be more than. It can't be equal like this. So F is no. Number 5, if 2 side lengths of a triangle are 5 and 7, What is the smallest possible integer length of the third side? This is a really good question. Because in our minds we would say 13. But it is not 13. It is not 13. Why? Because we can make 7 the biggest side.
Oh, it could be 3.
So we can make it 3, right? 5 plus 3 would be more than 7. So the shortest side would be 3 centimeter. Now if it said that those two sides were the shortest, then we would use 13. But it didn't say they were the shortest. So we're good there. If two side lengths of a triangle are 5 and 7, what is the largest possible integer length of the third side? It's almost the same question, but now we have to assume that these two are the shortest sides, which means that when we add those two together, right, we got 5 plus 7, which is 13. 12, rather. All right, yep, so that third side has to be shorter than that 12, which would make that 11 centimeters. That's even better. Bam. All right, we got to look at included angles, is what they're called. Included angles are angles that are sandwiched between two known side lengths. So, for example, if I had this triangle radical,
Why is there an S by the triangle?
to show that it's plural, angles. So, if we had these two side lengths radical, the included angle would be between them. All right. This green angle is included with those two sides. I mean, look, if we put on the third side on this, then this angle would be included with the 2 and the 3 mark side lengths. Yeah, that seems like a good explanation. An angle between two specific sides. So, for example, this 2 mark angle, radical, is not included between the 1 and 2 marked sides, because it's not between those two side lengths. Circle all triangles with side lengths 8 and 5 and an included angle of 32. So on this first one, we got the side AB and BC, which are 5 and 8. The included angle should be radical. But this one shows the 32-degree angle radical, so this one does not work. What about this next one?
Yes.
Well, yeah. So we got the length of 5, then 8, and then it showed the 32-degree angle radical. So we will cycle these. What about that last one? Well, here's the side length of 5 and then 8. The angle should be right here, but it is right here instead. So this one do not work.
Do not. That's not.
So number 2, this one says that we got the side lengths of 4 and 3, but we've got this non-included angle of 50 degrees radical. So the 50-degree angle has to be between the 3 and 4 side lengths. I'm sorry, this one should not be, because we're looking at non-included angles of 50 degrees. So this one, we got the side length of 4 and 3. 50 degrees is radical, which means it is not included, which means this would be one of the answers. What about this next one? So we got the side length of 3 and 4. 50 degrees is not the included angle, so this one works as well. What about the next one? So again, we got side lengths of 3 and 4.
It works.
50 degrees is not included, so this one, yep, also works. What about this last one? 4 and 3, but the 50 degrees is the included angle, so this one would not work. So that's part of 3. Circle all the triangles with two angles 90 degrees and 28 degrees with an included side of 6 units. So the included side will be sandwiched between those two angles again. What if you only have 3 pieces of information about a triangle, like 2 angle measurements and 1 side length? Is it possible to create more than 1 triangle? All right. So on these, the included side has to be between the two angles. So there's the 28-degree angle. There's the 90-degree angle with the 6. So this one is included, the included side length, because that side length is part of both of those angles. On this next one, we got the 90-degree angle right here and the 28-degree angle right here. The 6, though, is right here. So as it turns out, that's not included with those two angles, so it is not the included side length. What about this next one? Well, we got the 28-degree angle, then the 90-degree angle with the side length of 6. So yes, it is included on a these.